I get to know him well from his days in the faculty in theoretical physics, and
He used to be my boss.
so you can ask tough questions with Koonin on that. And chair of the Department of Provost, he's been part of Energy, and now he's at NYU in the Center of Urban Science and Progress. I'll tell him all about that work. So,
Okay.
there's a long list of awards that Steve has. I think you're aware of Humboldt, E.O. Lawrence Award, a variety of things, but without further ado. Oh, you should have gotten one of these. If anyone's interested in more information on this program, any grad students interested in applying, or just get on the newsletter, Julie, where's Julie? Over there. Handed these out and collect them if you're interested.
Okay. So, great to be back and see so many friends. I may have, in the early years, about 4 years ago, talked to some folks here about plans. 4 years later, the plans are starting to turn into reality, not exactly as envisioned, but in a very interesting way. So I want to tell you about the center that we've started at NYU, which is about the intersection of two simple but compelling trends. One is big cities, and the other is big data. And let me talk about the cities driver first. The world is urbanizing rapidly. If you look at the fraction of people in the developed world who live in urban areas, it's about 80%. In the developing world, or worldwide, we're now at 50%, and that number will go up to 70% by mid-century. We're adding urban residents at the rate of 50 million people a year, mostly in the developing world. That's the equivalent of 6 New York Cities or 5 Londons, depending upon how you might want to measure that. So cities are where the people are. They're where economic activity happens, they're where consumption happens, and they are where innovation happens. Some of you who are physicists may know Jeff West, another physicist who has gone bad into cities. And he likes to say that over the next several decades, cities will be the cause of our problems, for example, in sustainability, but also the source of the solutions, because that's where creativity happens. All cities have to be better for global issues, but any individual city needs to be as good as it can be, because we're in a global competition for people, for talent, for ideas, for capital. And being better has many dimensions. There's efficiency of the city, there's its resilience, there's its sustainability, clearly, but also quality of life, equity among citizens, and engagement of citizens with their city government. The other driver is big data. The world is getting very good very rapidly at acquiring, storing, transmitting, and analyzing all manner of data. This graph, which is about a year old, shows internet traffic as a function of time, and you can see it's gone up exponentially. Last year, even more so this year, there are twice as many devices connected to the net as there are people on the planet. And so sensors everywhere, things getting connected to the net. And the question is, can we put these two things together? And just let me take a moment for a little bit of personal story. How did I get involved with this? I spent about 8 years, first as chief scientist for BP and then in the Department of Energy, trying to change the energy system through technology. And I quickly came to realize that technology was a relatively feeble driver in the energy system, at least in the short to midterm. Somewhat disappointing to a technologist, in part because you're producing commodities, electrons or fuel molecules, and in part because it is a commodity business and it's the lowest cost of production that really matters. Technology is only one route to lowering the cost: operations, regulation, politics, and so on. What I came to realize, it is really the economics and the regulation, perception, behavior that drive changes in the energy system. And I thought, well, gee, I'll go work on that. And I quickly came to realize, to my horror, that I was talking about social science. And you know, what could I bring to the table? And the answer was, I realized the data. So I was going to go do data-driven energy policy. And then you ask, where should you be doing that? The answer is the cities, because that's where the people are. And then you quickly realize it's not just about energy in cities, but it's about everything that goes on in cities. And so I came out about 4 years ago, a little more, with the notion that I was going to go instrument a city in the way that a scientist or engineer would. I wanted information about the infrastructure, the operation of the infrastructure. Is the grid balanced, for example? The condition of the infrastructure, are there potholes in the road? I needed to know about the environment, obviously meteorology, noise, flora, fauna, all important. And most interestingly and most problematically, you needed to know about the people. Cities are built by people, for people. You can't study them without studying people. And so immediately we will, and we'll discuss, run into privacy issues. But if you take the privacy off, you want to know location, you want to know communications, economic activity, health, nutrition, you can go on and on. And the fundamental assumption behind what we're doing is that if you can properly acquire, integrate, and analyze data in all of these dimensions, that you can help make the government better, more efficient, more responsive to citizens, better planning, better operations and regulation. You can improve the engagement of the government with citizens. If people know that their bus service is only half as good as across town, then that changes your relationship with the government. The private sector. Everybody wants to know what's going on in cities, whether you're a retailer wanting to cite a store, you're an insurance company wanting to stratify risk, or you're a political campaign wanting to target your efforts. Knowing what's going on in cities is commercially valuable. And then finally, we're hoping, and in fact we are starting to change the way people do social sciences to go from well-curated surveys of 5,000 people every 5 years to methods that suck up data on 1 million people at once in almost real time. Okay, so let's talk a little bit about the data and where you can get it. Urban data have been collected for millennia. The word statistics has an origin in Latin, meaning of the state. And the Romans needed to understand how the various cities in their far-flung empire were producing and how much they should be taxing, and so they invented statistics. For modern urban areas, data have been limited in quality and sparseness, certainly difficult to get in real time. It's made it difficult to test hypotheses and turn this into a science. But it's these new technologies, the digital records, city records are now digital, and often they're open and available. Sensors, computing power, analytical techniques give you granularity, coverage, timeliness that you just couldn't get otherwise. I will spare you the quote from Lord Kelvin. So let's just talk about data sources. The city generates an enormous amount of data just in the course of its operations. Census, permits, taxes, all manner of sort of administrative data. There is transactional data, largely in the private sector, sales, credit card records, telecommunications data. There's operational data, the utilities, the transit system, the health system, and these days we have Twitter, blogs, Facebook, and so on, all generating some manner of data. We're seeing sensors everywhere. We have personal sensors, Fitbits, etc. We're all carrying around sensors of various kinds that connect to the outside world. My guess is that this room, if this is a new building, will have temperature, humidity sensors connected to the net. And then we have choke points, toll booths, building entrances, and so on. And then finally, there are opportunities, and I'll show you some of these. This is some of the things we're working on, novel sensor technologies, new ways to observe the city and understand what's going on. So I want to take you through a tour of some of my favorite kinds of data. You can get a sense of what is available and what's possible. I'll start with this example, which maybe appropriately for this audience is about energy efficiency in buildings. In 2009, New York City passed a law that required all big buildings above 50,000 square feet to self-report their annual energy use. How much electricity, steam, heating oil, so we'll come back to heating oil in a while, and natural gas did you use? And Constantine Contacosta, who's a professor of engineering at NYU and also our deputy director, is the principal analyst of that data. This is some of the earliest data from the first year. It's a histogram of energy use intensity. So how many BTUs per square foot per year did the building use? There are 1,150 office buildings in that sample. And what's interesting is that some buildings, big data is great at picking out outliers, use as much as 5 times the energy per square foot as other buildings. Now, is that due to what goes on in the building? Is it due to the building construction, the way the building is operated, or plain old misreporting? And one can start to dig into the data, the sample is big enough to ask those kinds of questions. That's a similar histogram for 7,505 residential buildings, think apartment blocks. And even here you can see that there are factors of 2 or 3 in energy use intensity over the sample. Understanding what makes those differences is the first step in trying to make them more efficient. Here's one cut at the data, just so you can get an example. Pay attention to the office buildings in which the energy use intensity is now plotted as a function of the year in which the building was built. This is a typo, it should be 1890s, by the way. And you can see that the newer buildings use much more energy per square foot than the old building. We think it's got something to do with the glass curtain walls that are there in new buildings and not particularly energy efficient. You can also start to do geographic analysis. This shows how much of the household income is spent on energy. You can get a sense of the geographic resolution that's available. And you can see that there are some families that are spending 25, 30 more % of their income on energy. Okay, different example now. The cell system generates call detail records, CDRs. And Mr. Snowden, a couple years ago, famously taught the world about that. Basically, these are the externals of a telephone call. What handset, what time, who were you calling, things like that. Nothing about the internal content, but just the external content. And a team of researchers at MIT, led by Mara Gonzalez, and at Stanford got from the phone company 500,000 CDRs in San Francisco and the Bay Area for 6 weeks. And you can use that data to start to understand mobility. So for example, this big plot, which is from a Nature article a couple of years ago, this street, East Hamilton Ave in San Jose, is fed by 51 different cell tower areas in the morning. And that street, Hickey Boulevard, up in Daly City, is fed by 12 of them. If you're the person managing or planning roads, this is invaluable data. The way in which you used to get it was to run a survey every 3 or 4 years, ask 3,000 people, where do you live, where do you work, how do you get to work, and then you got the data. This is, well, it's not real time, but it's clearly highly granular and very useful. Marta has done an analysis starting to look at some of the social science aspects from data on about 40,000 phones in Paris. She could find the fraction of the phones that had a unipolar path every day, namely they just stayed in one place, presumably home. Then the fraction that had a bipolar commute, home for work and back, various three-way patterns and so on. You can start to get a sense of how people move around the city. And you can make a model for it, obviously. Okay, different example, another mobility example. We're great fans of taxi data at Cusp. The Taxi and Limousine Commission that regulates the taxis in New York City mandated some years ago that every cab ride in the yellow cabs record the GPS start and stop, time, fare, tip, medallion, driver of every taxi ride in the city. There are 13,000 yellow cabs. They make 180 million rides a year. We've got now 4 or 5 years worth of that data. You got to clean it up a little bit. Some of the rides start in the East River, and clearly you've got to throw those out. But nevertheless, it's really interesting data set. Not only does it tell you about mobility issues, but it can tell you about psychology. For example, if the trip ends up in a rich area, is the tip proportionately more or less than if it ends up in a poor area? How do rides and fares and tips depend upon the weather or the way in which the sports teams are doing or things like that, all right? What's shown here is the first simple cut of the data. It's just the number of rides per day. for every day of the year for 2011 and 2012. You can see what we'll come back to is a kind of pulse of the city pattern in which the rides are high on Friday and low on Sunday. And then you can see various events. For example, this was Hurricane Irene in 2011. This was Superstorm Sandy in 2012. You can see Christmas, et cetera, et cetera. The city had some kind of half marathon going on over there, and so that's responsible for that anomaly. You can look in even more detail, again, pulse of the city. They took 1 week in May of 2011, 3.6 million trips, and isolated the trips that started at the train stations versus 2 of them, Grand Central and Penn, and the airports, JFK and LaGuardia. And you can see the number of trips over that week at 15-minute resolution, very repetitive, quite regular, although with some anomalies, more trips out of the train stations than the airports. But if you look at the tips, more tips out of the airports than out of the train stations. Presumably the cab drivers know this, but it's nice to see it. But what's more interesting is the regularity of these patterns. It's quite amazing. So, you know, it should be, we'll come back to regularity in a while. Recovery in the taxi system. This was a day before Sandy hit, and then the days post-Sandy, and you can see the number of rides starting to recover geographically. I was living down here somewhere, and it was a ghost town for about 3 or 4 days compared to the rest of Manhattan, which was running just fine. Okay, one other kind of data, and then we'll go on to some new technology. The state has about 13,000 lottery outlets, and you can get lottery sales geographically at 15-minute resolution. And these are some graphs that demonstrate, again, the regularity of that and the geographical location of the sales. And it doesn't take much insight to understand how regressive this particular activity is economically. The poor people are buying the lottery tickets. All right, different discussion. Some example of some of the new things we're trying to do at Cusp. Just about 4 years ago, Bob Rosner, who was a former director of Argonne as a professor at Chicago, distinguished astrophysicist, took me and my wife, together with his wife, one night up to the top of the Willis Tower. And I looked out from the Willis Tower over this flat Chicago landscape, and I saw all those lights. And I had grown up academically in a place that is one of the world centers of astronomy, and I'm starting to think astronomy as I'm looking at this scene. Lots of lights, different colors, almost all of them not moving. And what could you learn by using the techniques of astronomy to study that? A little bit more impetus came a few months later when I pulled this image off of the web. It's an infrared, thermal infrared image of New York City, the lower east side. And if you look carefully, so we're looking at heat now rather than light, and if you look carefully, you can learn a lot of stuff. So let's look at that building. Presumably all the windows are the same, but they are different colors reflecting the thermostat settings in the different apartments. So I can read thermostat settings. That's kind of interesting. I know that that building has got a data center in it, and so it's hot on the bottom and it's hot on the top and cold in the intervening place. So I have correlative data. And then just for fun, I know that set of buildings is a public housing project, and in typical New York fashion, the heat is turned up full blast and people open the windows to keep the apartments comfortable, right? So you start thinking, gosh, what could I do with this? This is pretty interesting. I have persistence. I can sit and watch one picture every 10 seconds or even more frequently. I have broad coverage from a single instrument, and I have high granularity. I can see individual apartments. So you start thinking about doing this with other modalities, and I'll show you some of that in a little bit. So this is our view from our offices. If some of you ever come to visit, we're in downtown Brooklyn, and that's the view of the east side of Manhattan. For reference, the Empire State Building is 3.8 miles away, so you get a sense of the geography. That's the East River in the lower foreground. And you can see the foreground is residential and the background is commercial. We are fortunate to have a LiDAR topography of the city. So we know the shape of the city's surface with 1-foot resolution over the whole city. It's about 15 billion points over the city, LiDAR shots. And so we can fuse that image together with the topography to identify every building in the scene. And so once we determine the XYZ coordinate of every pixel, then we can drop down to the map plane and tap into all of the city data. And so this is just that same scene painted according to the distance from the observation point, which is in downtown Brooklyn. Then that gets a little more interesting. Those are all of the buildings up the east side of Manhattan, of which we can see at least a part in the scene. And then we have the records for every one of those buildings. How big is it? What's their energy consumption? What goes on in the building? The demographics. And so you can make pictures like this, the same scene, now color-coded according to that energy use intensity. The hot ones, by the way, the red ones tend to be hospitals and recording studios, or broadcast studios. And we could also outline in black every building that's heated by oil as opposed to natural gas, and that will be color-coded. So we know what we're looking at. We started a project, Greg Dobler, who is, I think, well known to some people here in Santa Barbara. He's an astronomer. And he came, actually at Michael Dittmore's recommendation or connection, to come to urban astronomy now about 2.5 years ago. And Greg has been a main driver behind this. We started taking pictures with a tiny camera, 9 megapixels, a 1-inch lens. Every 10 seconds, I'll show you data for about 3 weeks in 2013. Total data volume in that case, 25 megabytes and about 4.5 terabytes of data. And Greg started analyzing this. We've been taking pictures ever since. We've now got about 2.5 years worth of pictures at 10 seconds cadence. Everybody says privacy, all right? Got to worry about that. So we went to the IRB, the Interinstitutional Review Board, who approved human subject studies. And their reaction is, why are you bothering us? Everybody looks in everybody else's window anyway in New York City. And in fact, I learned recently, New York City has the highest per capita sales of telescopes and binoculars of any place in the country. All right. But you know, we are a public institution, we're in the public eye, and so we agreed to limit the number of pixels on the closest windows to what you see over there. So that's native resolution. I like to joke it looks like Z equal to 3 galaxies. And you can't see anything with that except
the lights on, the strong lights, we get a better
we get, yeah, we could, can we close some of the lights? Yeah, that'll be good for the movie coming up. We'll try. Okay. We also do all our analyses aggregate and de-identified. So the human doesn't know what particular window we're looking at. We're just interested, as I like to say, the shape of the haystack, not the needles in the haystack. This is a movie, Timelapse, through one day. Residential foreground, commercial background. We'll see the Empire State Building go out in a moment. You can see the lights in the apartment buildings going on and off, flickering. If you correlate the color with what's being broadcast, you can get a sense of what people are watching on TV. So you want to do that. Dawn, and I'll just let it run through the full cycle. The sun goes through the sky, the clouds. You can see changing insulation on the buildings. We'll see some clouds. A big sun glint off of the Bank of America building in a moment. And then it goes on. Okay. So we thought there'd be interesting things to learn just by watching. So in the early days of this work, Greg picked out by hand 4,200 window apertures. You got to register all the frames because the camera's moving in the wind and so on. And then for each frame, we measured the brightness and then just plot the brightness of each. It's a light curve, basically, for those of you who do astronomy. This is one window. I have no idea which one it is and which night, I don't know. But you can see, big jump at about 7 o'clock, another drop at 9 o'clock, bigger drop at about 11:30, and then comes on again. And you can make up a story if you wanted to, right? Somebody came home, turned off the TV, turned off an interior light to watch TV, went to bed after the evening news, and then the baby wakes up or insomnia or something like that. And so you can start to analyze these curves. When does it look like the big off, as we call it? People went to bed, or the big on when things turn on. And then you can make histograms of those, or plots, every night for 3 weeks. Sometimes, just like real astronomy, we get clouded out, or we have equipment problems. And again, the upper graph are the offs, and the lower graph are the ons. It's a pretty regular pattern with some differences on the weekends versus the weekdays. You can start to analyze, hopefully this is a proxy for energy use. We've not demonstrated that yet, but that's what you'd like it to be. We could also start to analyze behavior. You can take all of the residential windows for one night and simply plot them according to when it looks like the light went off. And so this is the cumulative of those upper histograms. Then you can take the same ordering but plot the Tuesday data. And you can see that things get scrambled. So the lights don't go off at the same time every night in each window. But if you reorder the Tuesday data, it looks a lot like the Monday data. So the city in aggregate is reproducible, but the individual windows actually decorrelate about an hour per day. We get enough data, we think we can start to build models of sleep-wake cycles. Right? Again, passively, synoptically, and with high granularity. Okay, then we discovered something interesting. Actually, this is Greg's discovery. Daytime, 3 frames spread over a minute. This is the first frame, the second, the third, second, first, second, third. I'll run it as a loop now, you can see that. And sure, you see the traffic running on the highway, but if you watch carefully in the middle, you will see something happen. See that big black cloud come out? So, this is what it looks like if you subtract the background off. You can see it quite clearly. A boiler, an oil-fired boiler fired up, releases a big black cloud of stuff because the stoichiometry is not any good at all. And that's what it looks like if you catch it from a neighboring building, a window. It, of course, disappears after a while. You can't see it from street level, often. And this is the biggest source of PM 2.5 in the city, not the diesel, but the heating oil. And so great interest in regulating this. And so we've got a way now of watching about 1,000 buildings in this scene passively and determining, repetition rates, who's doing it, quality of the heating oil if we turn on spectroscopy to watch when the plumes appear and so on. So the environmental protection folks are actually quite interested in this particular application. Okay, couple thoughts about the big science questions. You can imagine applications, I'll show you some more in a bit, but just for science, this pulse of the city, the physiology, it happens in almost every variable you look at. I've shown you the taxis, you can look at the lights. So you want to know what's normal for the city. How variable is it? The city happens every day. Can I build models of correlations between these various variables to understand how fluctuations might propagate from one variable to another? How does it respond to perturbations? If a road closes, for example, how does that affect traffic around it? If a park closes, how does that affect economic activity around it? How predictable are things? You'd like to get to the point where you can do a weather forecast for the city as a whole. It happens every day, and you should be able to exploit that. And then, another science question is how do the macroscopic observables of the city arise from the microscopic decisions that people make, either individually or through organizations? That's a satellite photo of Paris at night. It's got a particular shape. Again, it looks like a galaxy, sort of. Scaling laws for cities that the Santa Fe School has been promoting. The physical structure, how does that arise from the behavioral decisions that people make? The science is nascent enough that this is about as far as anybody's gotten in trying to figure out what the big science questions are. Okay, section break. Let me talk a little bit about the Cusp Partnership. We were formed in April of 2012 as a partnership between 6 universities, NYU in the lead, but Toronto, Warwick, CUNY, IIT Bombay, and Carnegie Mellon. Since some of those partners have emerged as strong partners and others have essentially dropped off the radar screen. A set of industrial partners, most importantly IBM, Microsoft, Xerox, and Con Ed and National Grid. Con Ed is the electrical utility in New York City and supplies a lot of the natural gas. National Grid supplies some of the natural gas. Not listed on this list, but also a senior partner in what we're doing is Lockheed Martin Corporation. I knew that the national labs had great talents in dealing with data in simulation and sensors and so on, and so I brought in 3 of the national labs, Livermore, Los Alamos, Sandia, and also Brookhaven, which is the local New York City national lab. And then, most importantly, I think, we were created in a partnership with 13 agencies of the New York City government, ranging from buildings through sanitation, fire, police, environment, and so on. The MTA, which runs the subways, the buses, and the commuter railroads in New York City, and the Port Authority of New York and New Jersey, which famously, everybody keeps reminding Chris Christie, runs the bridges in New York City, as well as the airports and the port itself. So these folks give us data, they give us problems to work on, and the opportunity to demonstrate solutions. We are an educational operation also. Right now, we offer a Master's of Science in Applied Urban Science and Informatics, full-time, part-time. There's a track that's a little bit less quantitative, and we do certificates as well, which are even smaller programs. The graduate program is a mix of data science. I would say about 30% data science, 30% urban, how do cities work, how are they governed, what are the problems, and then another 35% of a capstone project in which the students work in small teams together with a city agency and a faculty mentor on a project for about 4 months or so. This is what the curriculum looks like. For those of you who are interested, perhaps, in joining us as a student, Julie Zimmerman over there will be around afterward and can provide a lot more detail. You can find some of this on the web as well. That was the first class in 2014. Bloomberg was still the mayor. We had 24 students. They dropped to 23. We were all not that skinny, actually. That was the second class. We had 63 in that class, and 6 of them were New York City employees doing the program part-time. That's a wonderful thing because the students get the training, the classes get the experience of having a city employee in the class. One of them, for example, is an active duty cop. And then we get friends when these people go back to the agencies and they can feed us data. That was the class that started back in August. You can see we've grown from 24 to 63 to 87. And again, 10 of those students are New York City employees. So it's really interesting. The class has got a great diversity of backgrounds, everything from physical scientists, data scientists, social scientists, urban planners, aspiring politicians, and so on. They're all quantitative, and they're just a great joy to teach. The students do RAs during the year. You get a sense that there are a lot of things, research things they're involved with. Some sense of what the Capstone projects looked like last year. This year we're going to have, what, about 20 of them? And we're in the process of defining and forming up teams and so on. And it's everything from a high-res economic map of the city using tax data, and employment data, assessing quality of parks, trying to understand and help the sanitation department. You can go on and on. Some of the alums, you can get it. So Alex Cholis-Wood, who was in the first class, he was a studio artist and had never written a computer code before. He turned out to be the star student in the class and is now some big shot analyst in the police department. Warren, well, you can read these as well as I can. They're real people who've been through the program. All right, enough about education, back to research a little bit. Having grown up in Caltech, one of the things I realized is that facilities are really important for research, not so much buildings and laboratories, but unique instrumentation or capabilities that both attract forefront faculty, let you do forefront research, and help nucleate faculty around common problems. So think accelerators, detectors, telescopes, seismic networks, and so on. And so we created, or are creating actually, 4 such facilities to help do urban science. One is the data facility, the second is quantified community, a third is the Sonic project, and the Urban Observatory is the 4th. I will say a few words about each of these and then just show you a little bit more research results toward the end. The data facility was and is becoming omnivorous ingestion of all manner of data about New York City. So records data, sensor data, public, private, closely held, open. You need to make the data interoperable. So for example, there are 4 different definitions of buildings in New York City. There's the lat long, there's the street address, there's what's called the BIN, the building identification number, and there's the tax ID, which is called BBL, borough, block, and lot. And of course, these are all not commensurate with one another, and just learning how to disambiguate and map from one to the other is not trivial. Similarly, we talked about cleaning up the taxi data. So can we make all that work together so you can do that? The catalog is starting to be built. It's being built by Professor Julia Lane, who is a labor economist, but her expertise is in national statistics and building such data facilities. There's a URL that you can start to get a look at the catalog that's up there and some of the tools that are available to deal with these data. This is a stunning figure. It's about 3 years old, but it's illustrative. When Bloomberg became mayor, about 4 years before the end of his term, he hired a guy named Mike Flowers to be the first data analyst for the city. And Mike's job was to aggregate all of the data feeds around the city and put them all in one place. Never mind cleaning them up or making them work together. Let's just get them all in one place. And Mike managed to do that. That facility exists. It's called DataBridge. We have access to that. Not unfettered access, but certainly all the open data and some of the closed data by agreement. And so 311, fire department, weather service, sanitation, you can go on. Some of this data gets updated daily, and we get it. Others of it is updated every 6 months or so. Right? And part of our job is to help the city learn how to exploit this data and train people who are capable of doing it. It was no mean feat to be able to do this in the city. Bloomberg, of course, is a data-driven guy. But even so, I like to say the second most basic human urge is to hoard data. Okay? The city agencies do it because it's turf, it's power within the government. The private sector does it because it's commercially valuable. And yes, the academics do it also because it's publication rights. Right? So everybody hoards data. We spend a lot of time with lawyers and data sharing agreements, as you might imagine. Just to get a sense of what's out there by national statistics, this is census data, and what's plotted is the Gini index, which is a measure of income inequality, and it's from the American Community Survey. And I put it up just to show you the kind of spatial resolution you can get with this data. We want to be out there in the forefront on privacy issues. We sponsored a book 2 years ago, was published, on how you deal with privacy in an academic setting with big data, and lots of authors, lawyers, ethicists, and computer scientists. Second facility, quantified community. The vision here is to create a community of order 10,000 people that you can fully instrument in the same way you take a slice of the brain and want to fully instrument every neuron so you can understand what's going on. It's realized actually in several different ways now. The first is in a development that's called Hudson Yards, which is the largest commercial development in the country right now. It's on the west side of Manhattan, the northern end of the High Line. We're partnering with the Related company to instrument one of their buildings, which will open in about 2 months. And obviously building operations, but also occupancy, environment, and so on. You can make a long list of these things. Another instance of that is that New York City wants to create 5 neighborhood labs where you would instrument the street, video, Wi-Fi, Bluetooth. The big belly trash cans are all online, and they can tell you when they're being used. The merchants will cooperate with retail sales and so on, and try to get a good synthetic picture of activity on the street. I'll say a word about the sound project, which we called Sonic, Sounds of New York City. We built some, actually a couple of postdocs, very talented folks, built a set of acoustic sensors at about $100 a box that are good to plus or minus 2 dB. And this is what the city requires for noise code enforcement. And also created a machine listening technology that classifies the sounds that are heard. I'm not going to go through this, but there's the box. Okay, it's got a MEMS microphone on a stalk, a gooseneck, exfiltrates through Wi-Fi, and it's got a cheap board inside. We start deploying these next month at 100 sites around NYU. There are all kinds of legal issues, as you might imagine, about recording sound on the streets of New York. Actually, not video, but sound. And we're navigating all of those. It's not so simple. The machine listening algorithm is a typical classifier, although it's very good. It can distinguish in the audio stream between dog barking and siren and so on. You want this because you don't want to have to send the raw audio back to the database. That would be illegal, but if you can do the classification in the box and just send the features back, that's okay. Urban Observatory, I've shown you some of the synoptic things already, but I'll show you some other now synoptic technologies, which are kind of fun. We got a shortwave hyperspectral scanner. So this covers 0.4 to 1 micron in 800 spectral channels. So just like an ordinary camera takes pictures in 3 colors, this takes pictures in 800 colors at once. And from the spectral pattern of each pixel, you can distinguish different lighting technologies. So this is what a high-pressure sodium lamp looks like as a function of wavelength. That's what a fluorescent light looks like, and so on. And so Greg, again, this is some of Greg's work, took a picture of the region around Manhattan Bridge and was able to type every one of the lights. So we can watch, again, passively and synoptically the penetration of lighting technologies into housing. When do people switch from incandescence to fluorescence? We can also look for rebound, right? If I gave you a more efficient light, you might be tempted to keep it on longer, and so negate some of the efficiency gains. Clearly, you can study that in the wild, so to speak. We're not there yet. We actually this was done with a borrowed instrument about a year and a half ago. Greg just won some award some months ago and ordered, and we're just about to take delivery this week of our own hyperspectral scanner, and we'll be able to start doing this kind of work more broadly. I'll close with another physics-style example. We did long-wave infrared imaging of Manhattan, working with the Aerospace Corporation using an instrument owned by the Air Force, but built by Aerospace. We sat for 10 days in Hoboken and watched the west side of Manhattan from the Battery to 59th Street with an instrument that covers 7.6 to 13.6 microns in 128 spectral channels. Why is that interesting? Because in this region of the infrared spectrum, every simple molecule has a unique spectral signature. And so you can observe and identify plumes of stuff coming out from the city and just sit there and watch the way the city evolves like that. So just a little bit about this. This is the geography. We sat there in Hoboken and watched from 59th Street down to the Battery. The scene, if you ever visit New York City, it's well worth a trip to Hoboken. It's 10 minutes on the PATH train, as it's called. And that's the scene, or at least a part of the scene. The Empire State Building is 2.1 miles away, and the waterfront is 4,000 feet away. You're right on the river, and the whole of New York City, or at least the whole of Manhattan, is right up in front of your face. This just demonstrates that we can do for that scene the same thing I told you about from Brooklyn. Some tourist pictures. So the team from Aerospace is based in Redondo Beach, and they showed up on Easter Sunday. It was pretty cold, but they were still in California dress, right? Doug will recognize maybe Kerry Buckland. There's the instrument, there's helium, keep the instrument cooled, and after a couple days of visits to the hardware store, they were able to set up a tent and a stable platform from which the instrument could watch the skyline. The instrument that we borrowed, rented, is this one, which is about in the middle of a 20-year development funded by the government of such instruments. Why is the government interested in it? Well, they usually fly in airplanes, as you can see, and they're for looking at chemical plumes coming out of places where you might not be able to get to on the ground, like deserts and jungles and things like that. Okay. Think drugs, proliferation, etc. This was some of the first data that came out of the machine. And the top, these are not spectrally resolved images yet. This is just integrated thermal IR, so all of the colors are together. And this is one image, and then an image taken actually about 2 minutes later rather than one. And the difference between them. So what do you see in the infrared? Well, we see some hot plumes coming out of buildings. Right? Presumably vents. Actually, if you look at this building, you can always see some steam coming out for some reason. But then we got real interested in that thing over there. It's not there at the beginning and it's there afterward, and what is that? So we have building ID, and so we can look, we can go to Google Maps and just look there, and it's that building, which is, houses a fancy Italian restaurant. But you can see, more relevant for this discussion, the 8 cooling towers up on the top of the roof. And we're pretty sure that we caught a cooling tower turn on. So suddenly I've got a way of watching the HVAC systems operating for lots of buildings at once. Sort of interesting. When you get infrared data, there is some confusion between the emissivity of the surface and the temperature. There are algorithms, if you have wavelength dependence, to separate it. This is an example of one such separation. The temperature of the building is real important for urban heat island studies. So one would like to be able to do that. And then, okay, so now we turn on Spectral ID. This is the thermal image for reference. And that's a span that shows ammonia. So we found ammonia coming out of the sea. We think it's due to what's called the ammonia slip reaction, in which you mix ammonia with the exhaust from a gas turbine to reduce the NOx. And if you don't get the stoichiometry quite right, you get that. We see diphloroethane, we'll come back to that in a little bit. How is it done? This is the spectrum of 1 pixel. The red is the template for ammonia as a function of wavelength. The middle is the fit to ammonia, the residuals, and then you can scan through a library of order 1,000 compounds to find the ones that fit. And that is the way the ID is done. We see CO2. You can't see cold CO2 because the atmosphere is too thick, but you can see hot CO2, and we found it coming out of that building. Presumably somebody's burning gas or something like that. It's coming out. We did an experiment we couldn't resist. We got cans of this stuff, which is computer screen cleaner, or air in a can. It's diphloroethane, and we sent 3 graduate students out to the West Side Highway, or the piers, and we gave them cans, and we said 1, 2, 3, go. And if I can find the cursor, we'll show. Whoops, let's go back. Why can't? There it is. So you can see the release pretty clearly. The 2 on the left were actually at the end of the pier and so got blown away more quickly. The one on the right was at the foot of the pier. He also had 2 cans. Okay. I wanted to send him up to the Empire State Building to try it, but we thought they'd get arrested. So, we see lots of Freon. Freon 22, methane. It's illegal to purchase this chemical. It's illegal to build refrigerators anymore that use it, but if you're legacy, you can still use it until 2022, I think. And we were surprised to see this kind of haze of this stuff all over Midtown. We would need two sites in order to start to geographically track the sources, but at least you can see it's visible. It's also seen in both emission and absorption, depending upon what the background looks like. This is a long list of chemicals that we saw. We've not tracked down any of the sources yet, but you can get a sense that there's a lot of information there. And I had been hoping to find a drug lab, which would have demonstrated to the cops that this might be useful for what they're interested in. We didn't do that, at least not yet, but we did find an acetone plume. That's a scan for acetone over about 3 or 4 hours in an afternoon. We saw this pretty regularly. You can see the plume in the left middle there. And so what was that? I thought nail salon instantly. It turns out, of course, we have building ID in geographical locations. So it turns out we ID'd it as 677 Washington Street. At 679 is Couture Cleaners, and they advertise on their website they're a dry cleaning establishment with on-site dry cleaning, and so we're pretty sure we saw their acetone. I think it's perfectly legal, but clearly this is a way of monitoring illegal emissions, whether it's intentional or fugitive. Okay, wrap up, what are we trying to do? What does 5 years look like? We're now about 3 years into operations. You can see we're starting to get a sense of what urban science means. We're creating a center, nucleating a community of people trying to do this, building some of the facilities. We're starting to execute projects that the city cares about, getting the trust of the city. You can't do this without a close partnership with the city government. So far, we've graduated 80 students. We'll have 150 or so by July of this year. We've got some commercial technologies in the pipeline. You've seen a few of them. And then change the social sciences. And then finally, start to franchise this globally. A couple months ago, we opened up a Cusp London in partnership with Warwick and King's College, and it's focused on health and well-being. King's has got a wonderful hospital system, together with the NHS, all kinds of interesting data in the UK. So that's it. Thanks for your attention. I'm happy to take some questions and comments if we've got some time.
We have a microphone so we can capture this if people have questions. Go ahead, Eric.
That was really fabulous stuff. And obviously there's a lot of potential for this to do some really important things for society. I want to go back to the potential nefarious uses, though, and looking at, for example, New York being a financial center. You can imagine getting the pulse of the financial center and saying, when there's a big trade coming up, the employees of XYZ private equity happen to go to this restaurant and have drinks late in the evening. These kinds of patterns could potentially quite be used for things that we really wouldn't want them to be used. How does one think about those kinds of problems and identifying patterns that could be used by selected individuals when they do subgroup analysis?
So early on, we thought about watching the lights in the financial center with high granularity would be an interesting thing to do and correlate it with trades or market movements. I don't know, the people in the financial business use all manner of data that they can get, right? And why is this any different than other sources of data that people use? If I were an employee of, I don't know, Goldman Sachs or something, I might want to be a little bit more careful about my patterns of life, if somebody can really track me. But, we're not doing that. I'm not watching individuals.
I'm not saying that you're doing it, I'm saying that
Somebody could
do
it.
it.
It could be done.
Some of your graduates might go off.
Sounds like a business opportunity.
I wondered if you had access to the smart meter data, and if you could sort of correlate signatures in the smart meters to what you'd see optically, like plumes, something turning on or off.
So we're working with Con Ed to get access to it. Clearly, we need it with high spatial and temporal granularity, and we've got to, frankly, convince them that we're a trustworthy enough partner that they can let us take that data out, or alternatively, bring that data in. Clearly, if I can do a light energy use correlation, then you could export this to other cities that aren't as data rich. I mean, imagine doing this kind of thing in Bombay, for example, or Lagos. That's why I like these synoptic technologies. You don't need all the infrastructure to be able to do something useful. For power companies, just knowing when outages happen is very valuable for Con Ed. At least there, I don't know what it's like in San Carlos, but somebody's going to pick up the phone and call the power company and say, my lights went out, or my lights were restored, for them to know what's going on. Clearly, if we're watching sections of the city, we can tell them that kind of information. You could also imagine playing urban fire tower, right? I'm watching in the infrared, I see some window flare up, and you know, it's not somebody opening another door, but in fact it's some fire and do that kind of thing.
So New York spent a lot of money getting this data bridge thing together and getting all this data started for you. Is there, if you go to very small or cities that haven't invested like that, if I don't know, Allentown or something tiny, is there a baseline of, is there any data at all at that level, or would you be starting from piles of paper?
So if I'm the Allentown city operator, or am I an academic wanting to study Allentown, or both?
Or if you are both of those people trying to partner up and figure out what you can do.
I mean, this informatics for city operations is something that is spreading rapidly around the U.S. It's there in Europe, and other cities like Singapore is famous for this. The cost of entry is getting lower. Allentown particularly, I don't know. But one of the things that is spreading, particularly in the U.S., is the whole academic science and engineering of doing urban informatics. The White House had an event in September trying to publicize all of this, and there has formed up something called the Metro Lab Network, which is at least 20 cities and their universities who are partnered in ways similar to which we're partnered with the New York City government. So Chicago and something called Urban CCD, the Urban Center for Computation and Data, is a sister center for us, kind of the same magnitude and spirit. So that's the city and the university and Algar National Lab. In Boston, there's something called BARI, the Bay Area Research Initiative. LA's got aspirations like that. So Pittsburgh and Carnegie Mellon are pretty far along in this. So it's coming. And as you can see, it's an interesting scientific subject as well as something that's got lots of practice.
Thanks for a great presentation. I also wanted to comment on the NYC data bridge. I mean, when I saw that graphic, I thought I can imagine, you know, this making a great deal of sense for data management, you know, analysis, et cetera. But it instantly struck me as you know, probably, you know, a question of also high risk in terms of breach, hacking, et cetera. So I just wonder how that emerges in your work. Yeah.
I don't know what the firewalls are and protections for the closely held data sets. New York City puts up about 1,100 data sets, opendata.nyc.gov. They're not curated, not clean. They're a dog's breakfast of stuff. Some of them are very useful. The most interesting one is, a useful one, is called Pluto, which is the public land use and tax output, which is all of the tax data for every building in the city. Okay? And that's very useful. Some of the others, you know, restaurant inspections and so on, less well used, park maintenance records and so on. But some of that is out there. But clearly the health data, some of the tax data are not public at all, and those are more closely held, I'm sure.
Thank you very much. A term flashed up on one of the charts, waste identification or something to that effect. What is that?
The city would like to know, well, first of all, you have to understand that the waste rubbish problem in New York, or system, is very complicated. The city picks up the residential waste, the business waste, whether it's office buildings or restaurants or whatever, or commercial carting services. And so it's pretty fragmented, first of all. The second is the city feels it's not recycling enough of the trash it's picking up. And so we'd like to have a better predictor of what the recyclable fraction is, so that we can start to promote recycling in those sections that are not. So basically it's a characterization of the waste stream at pretty high resolution, let's say a couple block by a couple block.
Steve, thanks. That was very clear. What is your vision for the research aspect of your center over the next 10 years? You're going to do a better job on Manhattan. You're going to branch out to other boroughs, other cities.
So, Doug, as you know, you've been up to the Space Aquarium. I showed you a lot of data for the Manhattan view. If you look out the other side of the building, it's a much flatter landscape, 8 miles worth of Brooklyn. And whether these methods, what we will learn from these methods, whether they're applicable or not, to a relatively low-rise cityscape, remains to be demonstrated yet. It's, of course, in the works. I'd like to have multiple views of things so we can start to triangulate. We can see buildings on multiple sides. And I think the real gold is in the correlation with the records data. So energy proxies is where I'd like to get to. We're working on that. We're about to install a second site on the Bank of America building, which is that slopey building. Why is that? Well, the Audubon Society is interested in how the city lights perturb the migratory patterns of birds. The birds come to land in Bryant Park, which is next to that building, and they sometimes crash into the buildings, so we can get, it sounds grisly, kill counts, because people go around in the mornings and pick up the bird carcasses, and we can start to correlate that with the lights. So it's sort of interesting.
Steve, this may be a slightly politically incorrect question, but Data Bridge was started by Mayor Bloomberg, and there has been a pretty impressive change of mayor in New York City. Have you found the same sort of, and this, what you're doing is very political, so have you found the same sort of openness in the new administration?
It's a wonderful question. As you may know, we have talked, we were very worried about the election a year and a half ago. We are a creature of Bloomberg. And in fact, it's turned out to be much better than we ever would have imagined. By and large, City Hall sort of ignores us. I think they know we exist, but okay. The Mayor's Office of Data Analytics, which still continues, they're a very close partner now because we've got some substance to deliver to them, which we didn't have a couple of years ago. But more importantly, the analytical fervor that Bloomberg started had filtered down into the agencies. And each of the agencies has now got an independent analytics shop. And we wind up talking mostly to those folks, which are much better than talking to the folks at the top, you understand. What power do they have, right? So much better we're talking to career people. And the hope is that we will place students in all of those shops and get a better foothold. So it's pretty good. All right? I think we've reached the end. Again, Julie is somewhere. And if you're a student and are interested in finding out more, there's information. Okay?